Testing. Okay, good morning and good morning. Good afternoon to everyone. Just past 12. So any question from last lecture or assignments? How you guys go with your assignment? How's your progress coming on? Mine? 昨天有 meeting， 我也是有 meeting 啊？今天呢？今天所以你 meeting 跟我 meeting， 我没有 meeting。我的空，什么时候？等下3点哦。3点钟，点到4点，我在 office。Okay, it's okay. We can discuss again tomorrow if anything extension or what. Yeah. So what have we done yesterday? Okay. Oh, okay. Before that, if you notice, if you look at the course information, okay, and you notice how our progress, you might think that we are late. We are indeed late. Okay, we are indeed late. But I feel that we can pick up later. Okay, because I want to spend more time on these sequence stuff because and supremum because these are the basic for differentiation for integration. Okay, so later we will move forward faster. Okay, in terms of proof and so on, because this is like the first class, right? You see proper proof and you see how ideas are written down in words. Okay, how these ideas are written down. So I try to go a bit slower. Okay, so try and capture as much as you can. Okay, during this period. Okay, because later we will move a little bit faster. Okay, so recap what we done yesterday. So yesterday we have shown that if you have two continuous functions at a point, then you add them up, you take the sum, you take scalar multiples, you take product, you take quotient, they are still continuous at that point. Okay, and this will lead to every polynomial function is continuous. So how you build polynomial function? Okay, you take product of x, right? Scalar multiple of product of x, and then sum of scalar multiple of product of x. So you are using the operation that we prove that it is still continuous. If you start with a continuous function, so the continuous function we start with here is constant function and identity function. Okay, px equal to x is identity function. Okay, and then px equal to x squared you can think of as p squared x. P squared x. Okay, so you take product of identity function. So this is what I wrote here. Okay, so you really see this polynomial as some combination of functions. Okay or not? Okay. And then what? And then we prove that composition of continuous function are continuous. Composition is different from product, right? Product fg is what? Fs times gx. But composition fg, f apply on gx. Okay, so there's a difference between these two, product and composition. Okay or not? Okay, so we also prove that composition also give you, composition of continuous also give you a continuous function. So you see there are a lot of ways to build new continuous function, is it? Right. So if you start with the continuous function, you know, hey, hello, long time no see. If you start with continuous function, right, you can do this algebraic operation to get new continuous function. Okay. Okay, so this is what we have proved using the sequential continuity, right? So this is the upshot here. So you can take sum, you can take scalar multiple, you can take product, you can take quotient, you can take composition of continuous function, still continuous. Okay, at a point. Kind of. Okay. All right. Then the last thing we left is this intermediate value theorem. Okay, what is intermediate value theorem say? Suppose you have a continuous function. Okay, so the whole subtopic is about continuous function, and it is continuous on the closed bounded interval here. And you know that the two endpoint there is a difference there. Fa less than Fb. Okay. Then there exists an x in this domain closed interval AB such that fx equals to q. What is q? Q is something in between the fa and fb. Okay, so I draw this kind of picture here. Remember, blah. So what is the proof we did yesterday? We did two kind of proof, right? Anyone remember what proof we did? So let's say we have proof 1 here and proof 2 here. Okay, proof 1, what we did? We use the completeness of R. We look at a bounded above set, remember? So what's the bounded above set we define here? We look at all the point in AB such that f of s is less than equals to q. Okay, then we show that sup AB is the point that when you apply f, you get q. So, and then we prove that if you get sup f of sup A is the point that gives me q. Okay? Okay or not? On the other hand, what do we do? What do we do in the other hand? We use nested interval theorem here. Okay, we use nested interval theorem here. So what do we did? How we built this sequence of an, bn such that this length here, so the length here, how to write with length 1/2 and minus 1, is it minus 1 of sorry, e minus a, let me think, yeah, minus 1. Okay, so we are trying to make what this an, bn going shorter, and shorter, right? When n grows, 1/n become smaller and smaller and smaller. Okay, it becomes shorter and shorter. But last time we proved that if we have this kind of nested interval, we can find a unique point, okay, in every interval here. So there exists a unique x in every an and bn, okay, for all n. And then we said that, oh, this one is the s we want. Okay, so there are two ways to find this x here. Okay, so I give you this example here. You see how many times this graph passed through Q. Can you see how many times this graph passed through Q? 1, 2, 3, 4, 5. Right, 5 times. 1, 2, 3. Okay. Maybe it's not clear from this construction yet. How do we build this A and Bn? Remember or not? How do we construct this A and Bn? Write down. What is A1, B1 here? We just take A and B, the first one. Okay. How about the next one? Okay. How about we go about to the next one? How we go to the next one? How to go to the next one? We check what happened at the midpoint. Okay. If this point is less than or equal to Q, what do we do? Then we set the left endpoint to be this guy. Okay, we set a how should I write this? So let me think. Okay, so I should put like this. So okay, let me just continue in this way. So we set A2 to be A plus B over 2, and then B2 to be just B. Okay. And what else? Let's say this midpoint here is strictly greater than Q. What happened? Then we set what? We set A2 to be just A and B2 to be A plus B over 2. Okay or not? Hello. Okay. Then we do it inductively for AN. Okay, can you understand what this thing is doing or not? Okay, let me show you in this picture here. Okay, let's look at this picture here. Okay, let's look at this picture here. So the blue one is my F, okay? And then I have A, B in the domain, right? Okay, and then the red dotted line represent Q. Okay, so if I use proof 2, right? Proof 2, what does proof 2 say? You go to the middle first, okay? And then you check what is the F. Okay. If F of this point is less than Q, then I build an interval here. Okay, I build an interval here. So I build an interval here. Here is A1. Okay, and then B is B1. Sorry, B2. Okay, so this is the next one because we set A1 to be A. And then what do we do next? Inductively, do again. Okay, so I start with this interval, divide 2 again. Okay, I divide 2 again. Okay, and then what happened? If this point is greater than Q, then this become my new B. New B. It's a real new B. It's a real new B, right? The new B. Right. So it's a new, okay, it's a new B. So I mean, so this become my B3, right? And then I keep my A2 to be A3. And then you do the same. You divide half again, okay? And then you check, hey, whether this point is lower than Q or not. Okay, lower than Q, then I shift my left endpoint. If higher than Q, I shift my right endpoint. So you can see that the master interval I create, right, is slowly what? Converging to this point here. Okay or not? You see, so this proof 2 will give you this point X here. Correct or not? This X is the X that have X, Fx equal to P. Does it make sense? Make sense or not? Got question? So the closed interval here will surround this X, which give you Fx equals to P. Make sense? Okay or not? The next interval is nested around this point that give you Fx equal to P. Make sense or not? Okay. How about proof 1? Proof 1 says what? I take all the points such that Fx less than equal to P. So in this graph, what points are less than equal to P? Can you recognize or not? How many part is less than equal to P? Huh? How many parts? 3 parts, right? This part, right? Less than equal to P. This part, right? Less than equal to P. And then this part also less than equal to P. So these correspond to the domain point here. And then if you take this set, right, you see, okay, sorry, maybe the color too close, you cannot recognize. This one, close also. Let me change my color. Change to this color. Okay, so you correspond to the bottom. Okay, throw away the previous color. And I do this. Yeah. Wait, I do this one. Do this one. Still a bit hard to see, huh? Okay, I think is it better darker a bit? So if you look at this red pre-image, where is the soup? Soup is where? Where is the soup? Can see or not, you guys? Okay. Still a bit darker, a bit light. Can see, can see the dark red part. You guys see the dark red part? Okay, so where's the soup here? Supremum of this number, where's the soup? Where's the upper bound? Towards the right. Towards the right, right? So towards the right. So which point you will pick out here? Actually, you pick out the last point that give you fx equals to p. So in the proof one, you really pick up this last guy here. So this last guy here, let's call it soup A. Okay, so you can see, so let me draw some more line. Some line here. So you can see this two blue line here. These two proof pick out different point that give you intermediate value term. Okay, no. Does it make sense? You see, these two proof pick out different point, might pick out different point. Okay, so this is the wonderful of proof. The wonder of proof. Okay or not? So if you produce different proof, you might produce same result, but you might pick out different stuff. Okay, so this is the special of proving. Okay, can make sense or not? Okay, so different proof might lead to different different way of seeing the result. Okay, so I want you to appreciate proof. Okay, so 你一定要听人家讲，可以吗？ OK， 不要以为你全部你讲的都是对的。OK 吗？别人的也是对的，虽然他找到的东西。OK， 说虽然他找的东西不一样，但是也可以问。OK 啊，你一定要听人家讲。OK。All right, so this is a proof of about intermediate value theorem. All right, so any question up to here? So these are just recapping and then try to think more deeply what happening in the proof. Okay, so proof one, proof two, we use different result. I mean, in the end, it's still the same, right? Because when we prove nested interval theorem, we also use the completeness theorem, if I'm not wrong. Okay. Because completeness really give you the taste of a real number. Why real number can be like filled in infinitely many. Right. I mean, if you think about natural number, it's like discrete. Why when you add rational, when you add irrational, becomes a line then? This is about completeness axiom. where you can keep filling in, keep filling in, keep filling in. Point and point, between points, still got point, point between points, still got point, point between points, still got point. And there's no gap, literally. Okay, so far, so good. Okay, okay, let's continue. So we will prove one theorem before we say the F-string value theorem. So what's the F-string value theorem? You guys still remember? I mean, you guys keep using it in calculus. What's F-string value theorem? About maximum, minimum one. How you use in calculus? Calculus. How every time you find maximum, minimum, how do you like find it? Differentiate. Oh, okay, differentiate. I mean, differentiate. We will learn later also. After we learn differentiate, we will prove why you guys can use differentiation to find maximum minimum. Okay, but this extreme value theorem would says that okay, let me just mention it first. Where is it? Um, wait. Okay, so what is extreme value theorem here? Value theorem here says it says that a continuous function must have maximum or minimum value. But this is only true when you are on a closed bounded, closed interval. Okay, closed interval. Because you can think of one function, right? 1 over n. You can think of one function, 1 over n. Right, thank you. 1 over n is not continuous at 0. So you cannot find maximum there. Okay, keep going up to infinity. Okay, but if it is continuous on a closed interval, every point in the interval is continuous, then you can find maximum value and minimum value. Okay, which is this denote here F1. Yeah, FC and FD. Okay. Okay, later we will motivate this more. Let's prove a theorem first. Okay, later we will motivate this more. Let's prove this theorem. Uh, okay, so how do we find these maximum minimum thing? So let F small. Hey, you guys okay with this kind of thickness, or you guys want this kind of thickness? This one. Okay. It's like a chalk. Okay. This one. So let F be a continuous function. Okay. On closed bounded interval AB. Then something is stronger. F is actually bounded. Okay. If you are continuous on a closed bounded interval, right? Actually, you are bounded already. It won't happen like 1 over x like that. Okay, actually it is bounded, and moreover, there exists the maximum. So how do we find this maximum? We simply take the sup, okay, sup of every fy, okay, of y in AB. This sup here exists. Okay. So meaning if it exists and then you can achieve it, actually is the maximum here. Okay, you can find the maximum guy. Okay, so there are two parts here. So our first part, actually your function is bounded. Second part, you need to find this x such that the sup, such that it is equals to the sup when you take the value of f on it. Okay, is it clear what we are trying to do? Okay. Okay. So first, we will settle the boundedness first. Okay. So how to show it is bounded? So suppose it is not bounded above. Okay. For contradiction. Suppose it is not bounded above. Meaning what? Meaning. Sorry. Yeah. Meaning what? You want to say anything? Move on. Okay. So f is not bounded above means what? What is not bounded above here? The value of f are not bounded above. Right. So that is the set of fz such that z is in the closed interval is not bounded above. Right. You consider all the value of f not bounded above. So what happens here? So meaning what? Meaning what? Meaning for every meaning for every m in R, what happened? There exists a set in AB such that fz is greater than m. Correct or not? For every m, you can find someone that is greater than it. Then what? Then what can we do here? Then what can we do here? Then what can we do? Then we can form a sequence of divergent sequence, right? Can we form a divergent sequence? Divergent sequence. Right. For one m, I can pick a point greater than m. If I find greater m, I can find another point that's greater than m. Then I build a sequence of divergent. Sequence that diverge. Does it make sense or not? Okay. So I mean, for example, m equals to 1. Okay. I can find z1 such that fz1 greater than 1. Make sense? Then what can I do? I can set m2 to be fz1 so that there exists a z2 such that fz2 is greater than fz1. Because my set is not bounded above, correct or not? Because it's true for all m, right? So the first m, maybe I fix 1. Second m, I fix fz1. Then third m, I fix fz2. Then got the next one is greater than it. And then the next one is greater than it. The next one is greater than it. Make sense or not? Then I form a sequence of divergence, a sequence that diverge. Does it make sense? Okay. So in particular, any n in n that exists Sn in AB such that Fsn is greater than n. Okay. 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 I mean, what I claim here is a bit stronger, because Fsn is greater than n. Okay. But previously, mine is depend on Fzi. But you can choose between the maximum of fzi and n, then you can make sure that the next term is always greater than the previous term. Make sense? I think a bit doesn't make sense to you. Makes sense to me, but not make sense to you. You want to ask anything about this Sn here? Yes. Yes. Yes, it is monotone. Wait. Um, yeah, I want it to be monotone and then also fxn greater than n. Yes, both. Hmm. I want it to be monotone and also fxn is greater than n because it's easier for me to control later, maybe. Does it make sense? Okay. Okay. Got question or not? So here this f is increasing. Do I need monotone increasing or not? I think. Let me think. Actually, what I did is stronger, Joshua. I think what I did is a bit stronger, but um, here, here you could imagine that. Okay, so what I imagine here is something like. So what I imagine here is something like this, this, this. So maybe it's like 1, 2, 3, 4, 5 like that. But the claim here could be look something like 1, 2, 3, 4. It could look something like this, maybe this a bit, and then come back a bit, maybe go out a bit, and then maybe go out a bit like that. Not really monotone, but this sequence still diverge. Okay, but up to you lah. Anything you want to do. Okay. So at first, I think when I thought about this green point here, right, I want something to be a bit regular, but you could do something irregular here. Still diverge. Okay, no? Still diverge. Okay, still diverge. Although it is not like here monotone. Okay, but still diverge. Okay, no? Yeah, when we see this kind of graph, it's good. You know why? This is the point you can buy in your stock. Okay, no? Yeah, right. So when it dips, quickly buy. Later will rise on. Okay. No one get the jokes. Okay, it's okay. Right. Okay. So in particular, we can find this FSN that diverges. Okay. So, where's the contradiction? Where's the contradiction? Where's the contradiction? We found a divergent sequence. Did we prove anything like if every subsequence converges? Sequence of fxn. So, okay. So let me put down this claim here. What can we do with this sequence here? So the sequence Fsn diverges to infinity. So every subsequence also diverges to infinity. If sequence Fsn diverges to infinity, so every subsequence also diverges to infinity. So do you want to think about this? A sequence that diverges to infinity means that every subsequence diverges to infinity. You can think of you can think of what? The contrapositive of this statement. Suppose there exists a subsequence don't diverge to infinity. Okay? Maybe diverge to negative infinity. Or maybe just diverge. Or maybe converge. Okay? Maybe we take one. Let's say there's one subsequence converges. Okay? I mean, convergence, you can simply think there's a constant function. Okay, constant function. But you say that the previous function is like diverge to infinity. Can you happen that a sequence sometimes diverges to infinity, sometimes constant? What does this mean? This means this sequence just diversion is not diverging to infinity. Right? Because for every m, you still can find some point which is less than m, in particular the constant. I mean, for every m greater than the constant point number. Okay, no. Okay, try and prove this. Okay, try and prove this. Okay, I will provide the proof also. But this is the claim. So if the sequence diverges to infinity, every subsequence also diverges. Okay. Okay. Okay, so we're gonna draw contradiction here. Okay, we're gonna draw contradiction here. So, however, so this one we will prove in lecture notes. Okay. So however, the sequence of xn is bounded for. Okay. The way we build fxn, this Sn here is contained in the bounded interval. Meaning what? So you have a sequence in a bounded interval. You can use what? Bolzano-Weierstrass, right? Bolzano-Weierstrass says what? Any sequence in a bounded interval, what happened? Every bounded sequence have what? Convergent subsequence. So you can extract a subsequent that converges. Okay. There's this subsequence. Say yn. Okay, of Sn. That converges. Okay, converge to where? Converge to somewhere in between the interval. Some point in the interval. So you see, you have a subsequence that converge to some point in the interval. But my f is continuous. But since f is continuous at the interval, we will have what? F of yn converge to fy. Okay, in particular, what? In particular, fyn is a convergent subsequence. Okay. Just now you said that you diverge. Okay, you cannot have convergent. You cannot all your subsequence must diverge. But I found a convergent subsequence here. Okay, but I found a convergent subsequence here. Okay, so a contradiction. Okay, so therefore what? Therefore, we conclude that F is bounded above. Similarly, you can show that it is bounded below. Use the same argument. Okay, say that it diverges to negative infinity, and then you say that every subsequence must also diverge. But yeah, above, sorry, above. Okay, so similarly, if to show f is bounded below, you use a similar argument where you assume it is diverges to negative infinity first, and then you say that for every sequence that diverges to infinity, every subsequence must also diverge to negative infinity. Okay, and then you extract the subsequence again in Sn in a domain using Bolzano-Walsh, and then you found convergence sequence. Okay. Okay, so it's bounded above and below, and so it is bounded. Okay, so this is the part for boundedness. Any question or not about this part here? I will try to write down this claim carefully to convince you, okay, in the notes. But are you somewhat convinced that this has to be true? You have to believe first. If you don't believe, then you need to come up with a counterexample. Okay. Is it okay? Any question? No question? Yesterday I put out the lecture note quite late. So please read the part that we say that we make it a lemma. See if it makes sense to you or not. Okay, now please ask. Okay, so we have established that f is bounded. Okay, it's bounded. So we prove this using contradiction, right? So maybe you want to try and prove directly whether it is bounded or not. Can you go and find? Okay, can you straight away go and find the what? The upper bound and lower bound. You can try and prove. Okay, for every x in fx, sorry, for every x in closed bounded interval AB, fx is lower, smaller, less than equal to some upper bound, greater or equal to some upper bound. You can try and see if you can find it. Okay, prove it directly instead of using this contradiction proof. So to do that, you need to go and propose. You need to propose a upper bound for me. You need to propose a lower bound for me, and then show that every point inside there is in between the upper bound and lower bound. Okay. Next part. Next part, we want to find the maximum value, right? The maximum value here. See, where's the statement here? So I want to find an x in AB such that fx is equal to the supremum, okay, the least upper bound of every f value. Okay, how do we do this? So we want this sup thing, right? So how are we gonna do this? So here we say that f attains the maximum. Okay, because there's some point that realize this sup. Okay, there's some point that realize this least upper bound, namely x. Okay, so how are we gonna find this x? Like, how are we gonna find this x? How are we gonna find this x? So first, tell me, this sup exists or not? Sup exists or not? Why? What axiom or theorem tells you a sup exists? This one must know. What theorem tells you a soup exists? Huh? Completeness axiom. But completeness axiom need what property? What property? Sorry? Yeah, you want to find a least upper bound, right? But what's the property of that set that you can find least upper bound? I give you an empty set, right? What's the least upper bound? Nothing. So you need to start with a non-empty one. Okay, and then also a bounded above one. If not bounded above, then how to find the least upper bound? Right. So you need to non-empty and bounded above. Okay. So that's why we show that f is bounded first. Okay. So if f is bounded, then the set of f value is bounded above. Correct or not? Non-empty, because f is a function, right? Function defined on a b. Surely got some number there one, right? F of something inside a b. So it's non-empty, bounded. Okay, just now we spent a lot of time talking about boundedness. So this soup exists. Okay, soup exists. But the problem here is how to find the x that realize this soup. Okay, so the problem here is how to find the x that realize this soup here. Okay, how to find? So I know the soup exists already. I just don't know whether there's some point that apply to f get the soup. Try and think about it. How to find this x? Try and think about it. In the moment, let me write down what we have. How to find? Okay, so just now we said this x is non-empty and bounded above. So soup x exists. So far, how we find point? We find point using sequence, right? So far, right? So is there any sequence that we can play around here? I mean, we don't have sequence yet. How to talk about subsequence? So any sequence we can play around here. I think this is quite related to your assignment question, especially the last question. So you have a soup of x. Can you build a sequence? Soup definition got what? What's the soup definition? The third one. I think is the most useful one. I mean, to most of the case. For every epsilon that exists, the A epsilon such that A epsilon is greater than soup A minus epsilon. So meaning what? When you make the epsilon smaller and smaller and smaller and smaller, you will get A epsilon closer to soup A, closer and closer and closer. Then you can build your sequence. Does it make sense? Does it make sense or not? Let me draw a picture again. Remember, these things is very figurative. So let's say I have my soup here, soup A here. Okay. And then I get some epsilon here. Soup A means what? If I take soup A minus this epsilon, you can find some A epsilon here. Okay. If I make epsilon smaller again, let's say this one epsilon 1 already. So A minus epsilon 1. Then I can still find A epsilon 1, for example, such that it is greater than soup A minus epsilon 1. You can see a sequence here or not? Can you see a sequence approaching soup A or not? Can see or not? I can make my epsilon smaller again. I can still find an A epsilon such that A epsilon is greater than soup A minus epsilon. So I can keep making my epsilon smaller. Can you see that I create the sequence of A epsilon that's approaching soup A? Can or not? Okay. So what? So there exists here, there exists a sequence Sn of point in AB such that Fsn converge to soup X. Remember how we get what are the points in what are point in X? It is f of something. Okay, so f of something, I make it a sequence here. F of some sequence of point that is approaching to soup X in this case. So here I will write here is the definition of soup. So we are extracting a sequence converging to soup A. Okay, so this is, I think, if I'm not wrong, this is useful. This abstraction is useful for your assignment 3 last question, if I'm not wrong. I remember I wrote something like this. I forget where. Can't remember. But this step is very useful. Okay, very useful. Use epsilon to extract some sequence that converge. Okay. Okay, so you have a sequence that converge to soup X. Then what? So just now Joshua talked about subsequence, right? Okay, where does this Sn live? In AB, close bounded interval again. Means what? By Bolzano-Weierstrass, again, there exists a subsequence, there exists subsequence of Yn of Sn, Yn of Sn, that this Yn here converge to some point. Let's call it X. And I claim that this is the X we want. They converge to X. At the same time, since f is continuous, Fyn converge to Fx. Okay, you see, we got Fsn converge to soup X. We have subsequence also converges, but to Fx, not soup X. Last time, what did we prove? What did we prove? Conversion of sequence and conversion of subsequence. What did we prove? Remember? Let me see. Can I find it? Yeah, here. If a sequence converges, then every subsequence must converge to the same limit. So just now we have Sn converges, Fsn converges to sub S. And we have subsequence Yn, Fyn converge to Fx. Then these two limits have to be the same. Okay or not? So we prove that sub x is equal to Fx by using the convergence of sequence and convergence of subsequence. Okay or not? Okay, the two limits have to be the same. Okay, sub x have to be equal to Fx. Does it make sense? Okay or not? Because if a sequence converges, then every subsequence must converges and to the same limit. Okay, just now what do we have? Fsn converge to sub x. Fyn, Yn is a subsequent of xn, converges to where? Fx for some x in AB. So sub x and Fx have to be the same. Okay, so let me copy this down and then we write it out. Okay. So since Fsn converges to sub x, hey, why the icon stop? You quite pop. Okay. So if Fsn converges to F sub x and Fyn is a subsequence of Fsn that converges to where? To Fx. This x is given by Bolzano-Weierstrass. Then the two limit have to be the same. Okay, the uniqueness of limit. So by proposition, sub x have to equal to Fx. Okay, so this x here is produced by the Bolzano-Weierstrass. Okay, because you live in a closed bounded interval. Does it make sense? A question? Any question? Any question or not? Any question? Okay. Why convert to Fx? So let's back up a bit. So you see, so Fsn, right? Fsn converts to sub x, okay? And then we just look at Sn. Where does Sn live? Bounded interval AB. So this is a sequence in AB, right? So by Bolzano-Weierstrass, this Sn here has a convergent subsequence that converges. Okay, so you have Yn converge to x. Everything happened in AB, but my function is continuous there. You see, my function is continuous there, so I can consider Fyn converge to Fx. Why Yn converge to x? Because this is what Bolzano-Weierstrass tells you. What does Bolzano-Weierstrass tells you? So here is the axis x. What does Bolzano-Weierstrass tells you? Every bounded, no close, right? Every bounded sequence has a convergent subsequence. And then Yn converge to some point. And then this point has to be in the close interval AB. Then, sorry, say again. Can lah. Lah. I mean, you want dinosaur, tiger also can. I can convert to tiger, where this tiger is in AB, then FSN converts to F tiger, and then what else? Then sub S equal to F tiger. But I don't care tiger, elephant, or dinosaur, lah, but this tiger must be in the close interval AB, that's all. As long as it's a point inside close interval AB, that's all. S is a name only. You get what I trying to say? Where's the X? No X here. XN is not X, so don't confuse. X is a new name. From scratch? What do you mean by from the top? From beginning, so you mean the sub X stuff, right? How to prove sub X equals to Fx for some X. So there are two part of this statement, right? So let's prove the second statement. Okay. So what do we want to do? We want to show that there exists some X. Don't know what X. Some X. As long as this X is in AB, that's fine. This is the point of this X. I can put tiger, elephant, dinosaur here. Okay. Okay or not? Okay. So what's the whole step again? Okay, let's recap what's the whole step again. So there are few things happening here. Okay. First, of course, you need to show some existence of point. Okay. What is this X trying to do? When you evaluate Fx is equal to this soup. But this soup exists or not? If it doesn't exist, can never equal, right? So it must exist first. So there are a few things to do. You need to show that soup exists. Okay. And then you need to show that there's some point Fx equals to the soup. Okay, this is the two things you need to do. Okay. So soup Y exists. Complete axiom unique, non-empty, and bounded above. So non-empty because you just simply take any point in AB, apply F, there's some point there because F is a function. And it is bounded above because we have proved that F is bounded. Not just bounded above, also bounded below. Okay, so soup exists now. Okay, now soup exists. So how do we find this X then? How do we find this X? Okay, so just now, our idea is we try to use Bogart-Weierstrass together with the convergence of the original sequence. But what's the sequence we're going to see here? What's that? So that sequence we're going to build is to use the property of soup. We're going to use the property of soup to build this sequence here. Right. If I give you a soup, you can produce me a sequence that converges to this soup. Why? I use the soup definition, the third one. For every epsilon, I can find some A epsilon that's greater than soup A minus epsilon. Can see or not? I fix some epsilon, I can find some point in this gap. So meaning what? I can make even smaller epsilon. Then I can find another point. Okay. So I make smaller and smaller epsilon, then I can build a sequence that converges to soup. Okay. Can you understand this part? No? You need to get this statement first and then see why is it true. Can see this statement, this part here. Use soup property to build a sequence. This part. Can everyone understand this? You take an epsilon, you fix one epsilon, maybe 2. Okay, find A2. Okay, and then you pick a smaller epsilon between soup A and A2. And then find another A3, A4, A5, A6. Then you can make a sequence that converge to A. Okay, so this is the sequence that converge to X. Why is it Fsn then? Because these points are all the point that is the image of F for some Z. So we arrange it. Okay, so we have Fxn converge to sub X. But Sn itself is also a sequence, right? Xn itself is also a sequence. So in particular, this sequence here live in a closed bounded interval. So meaning this is bounded. If it's bounded, Bolzano-Walsh says what? Every bounded interval has a convergent subsequence. Okay, has a convergent subsequence. Converge to where? Converge to somewhere. But somewhere, where this point live is very important. This point live in AB, actually. Okay or not? It cannot converge something outside AB. Or there will be a contradiction. Okay, it must converge to something inside AB. Maybe this requires proof, because Bolzano-Walsh doesn't tell you where the limit lies. Right? Maybe this requires some proof here, but if converges to somewhere outside AB, then you will be in trouble. Okay, it won't converge to outside, something outside. Okay, maybe this here, maybe you can put as a lemma if you want to be clearer. Okay, so what to do here? You have a sequence that converges to X. Then this whole convergence here happening in AB. Then you can apply the continuity of F, where you get Fyn equals to Fx. Okay, no? And then just now we said that if a sequence converges, every subsequence must also converge to the same limit. So here, Fsn converges to sub X. Fyn is a subsequence of Fxn, also converges to Fx. So these two limits have to be the same. So we get sub X equal to Fx. Hello. A question? Question? Ethan, what do you think? Okay. Okay. Yeah. So there exists an S, meaning this X here, you just need to find one is enough. It is in AB. Maybe I think this is not too clear. Why is it true? But this point here also, let me think, can it follow from what we proved yesterday? Let me think, I think can. Okay, this is a similar result to what we discussed yesterday. If Sn greater or equal to Q, if it converges, it must converge to something greater or equal to Q, like that. But this one is two direction, less than equal to B, greater equal to A. So it's like combining the two results we proved yesterday. I mean, not proved, but we left as a lemma. I just uploaded this morning the lecture note for yesterday. So if you want to look of the proof of the lemma, I think it's the two lemma that we proved yesterday. I mean, in my lecture notes. Okay, because Bolzano-Walsh doesn't tell you it converges to where. It just tells you converges. But the point here, this X have to lie inside AB. So to be pedantic, you need to prove why this limit is inside it. Okay. So far, any question? Any question? I don't expect you to understand on the spot. You need to think about it more carefully. Okay, and then you come back and ask me more question. Okay, no? I don't expect you to understand on the spot, but you need to keep thinking about it. Does that make sense? Okay. Ethan, where's your brother? You get.
I know, but he haven't.
You haven't get out?
No.
Oh, you haven't submitted. He's not responding to my message. Send you. Yeah, you asked him to reply me. Okay or not? Any question? Any question? If not, let's take a. Should we take a break or should we continue? I mean, not continue, but one last thing. Maybe just finish up. So just quickly finish up with this theorem here. So from here, right, we can deduce that a continuous function on a closed bounded interval okay, you can find maximum and minimum. So just now, your proof is about soup, right? You can change the proof about inf. Okay, so you can achieve both inf and soup. Okay, so you can find this maximum point and minimum point. Okay. Similar in the intermediate theorem, value theorem. Intermediate value theorem, just now we assume that FA is less than FB, right? What if FB less than FA? Does the proof still work or not? Does the proof still work if FB less than FA for intermediate value theorem? Still work, right? Just that you go the other direction. So your everything of your construction, you swap it on. Okay. Yeah. Yeah. So this is actually this kind of like swapping this property is like an algebraic property. Okay. So it's like structure. So this proof doesn't change if the structure change. Doesn't change much, I say. Okay. The way to find it is the same. We still use we still use nested interval theorem, we still use completeness. Okay. Okay. If no question, then let's take break until 1:23. I could bring some snack if you like and take here to wake you up. Okay. So let's take a break.我刚喝饱了，有一些 and 还有就是有一些，你喝完了没？喝完了，等你那一袋呢？这是什么？环保袋。所以你是为了这个环保袋？不是，我是要带去。OK。什么？放香啊？也是啊，两包继续，就是我try一个，我本来想要 try 一个 strawberry 还是这个，然后我想一想，这个西瓜有一点酸。现在我知道这个会超过，OK。现在他讲的介绍一些，对不对？介绍一些 X， 然后再选这个。是吗？我哈。哎，拿这样分，对的，有点，对不对？但是我 try 看我没有吃过，等下我要 try 一下。
比如讲，那我来那个，那我就有新的一份，这是一个一个觉得，哎，这样子这个东西我在里面，我在里面。然后你看这边，它跟这个道路距离是180我跟这个，所以我设了200万这个西，
那你实力到还是什么？我也不懂哎。可以去看，它还可以盖回去吗？
的话，就对的话，我的有一个新的，
也还不错。
哦，要么就是有这个，要么就是有这个。然后我要再讲啊，因为epsilon 光就所有的epsilon epsilon 是 really decreasing。就是这边就是
还要开了吗？
啊，
不装。
因为这里到这边买的，
这个 mix 哦，这个是没有分太多种。
我都有。哦，这个不同的，
这分太多种。
有在这边，在这边，那就是
拿把提过来。
什么？
我这个都没有。
我这边，
如果我去了，
这个打过来，
好不好work？
如果这个我在那边的话，它是地图。
对啊，这蛮好用的。
会有会有这样说话的，
不是还有一个
减掉
那下是也是开放吧？好的。
还有那个把全
哦，一开始都是
哦，是啊，是啊，
哦，是这样，从上。
然后周三是那个 actual 的，但是下周就有一个，所以才快。
周三都是快他。
对，这是我的这样子。
都没做什么，我刚刚做也没事。
应该没问题，因为就是总会考到最后一个问题。
就是看到一道题，我先讲我觉得我 X 说，那些时候就想我看到他证明过没有，没有证明还在证明没，然后就不会的那个。
就是这样子。
太多了。
一开始看过，所以最好是历史啊，这个因为你们也是要用机械嘛，先历史吗？
还可以的吗？
对呀，所以你们要先历史，先历史先历史还比较习惯。啊？看不到一个一个历史。
就是他压我在这边，如果他有的话，如果他有的话，就选这边；如果他两边都有的话，就选一个；如果他只说这边，我就选。
会证明过的。
那个是在证，
不用再证一次了。
那个不用，那个不用。把 epsilon 如果可以把它讲成是for epsilon 如果
叫我心里就是一个
小 epsilon，
这个越来越靠近，那他就得 S 一个，因为刚才老师讲，得就是一个是一个3月。
我希望它能小于等于。
这个我没有证过。
哎，好难。
他是不难，现在。不难，不难，你就是用采购统计嘛。如果它大于0，
对，因为我看他有讲，我的单纯这个点个，对，就是所有加1会对。
没有，你就像我想要做一个底号，然后把这个
如果这样子，如果
那个更简单。
如果谁这样
如果它是你用符号多，
他就会越来越低。
这个
要先首先在这边，
慢点，我想好像记得有过，
然后找到一个
但是我不记得是属于哪个地方。
哦，
然后
找到一个
我记得是要
那谁，我再建议他。
对，我们波是等于零，
如果他
小于等于零，只是
选 x 度会是对，
我希望吧。
就他越来越靠近这个10啊。
你讲的对，我们的那个上面好像有一
哦，对，相似，对，有点像。哎呦，我那个好长哦，我可以别搞，你可以不要。也不需要 S 哦，为什么这个它每个整个每个肌肉很肌肉，
因为它的
这样子全部在。
下面
然后你呢？precisely object and truth. 对，
就是这个部分我明白了，但是又怎样讲，就是肯定是存在个 xn，I mean
存在这个 SN，
因为这个是在它的那个 x 的认识里面，它是存在sub s 嘛，是不是？
sub s 这个 a epsilon 在这个 case 是长成 f of something。
对，但是他在讲呢，好像自己是方程啊，自己是那个a to b 嘛，这样你就这样知道他肯定是有那个一个
因为你的 sequence 是在 fz1 fz2 fz3 fz4 fz5，
就是也就是怎样讲呢？就是他已经define好，他每一个 fx 它肯定是有一个 x point 在那里。
肯定，因为这里面的 point 都是有一个 z 来 realize 啊，肯定。
他已经一开始 define 好了，对啊，也肯定是有啦。他因为
我们的 x 是这么 define 的，因为这里的 sub s 这个 a epsilon 啊是要活在那个 set 里面，而我的 set 是长这样。
这样也有可能有其中一个 fz 它是 undefined 来的。
不可能啊，不可能嘛，对不对？因为如果 undefined 就代表我的这个 a epsilon 不在这个里面了哦。可是我这个 这个 sub 的 definition 是说 a epsilon 一定要在这个里面。
只能是在 fz 是 fz 啦，
在我的那个 set 里面呢，这个 set 里面的东西全部长这样。
我的意思是，比如说在它是 A B 里面，它在 A 和 B 的 interval 里面，每一个 point 都一定有一个 fz。还是还会有一个。
这个是对的，因为这是我的开头吧，它是一个 function on 这个上面，所以每一个点一定要有一个点的，因为这是 function 的 definition。
因为也是会有 function 是 undefined point 嘛，不是？就是 I mean 还是那个就不算是 function。
它不 define on 0啊，好像 e over n 啊，你这个 function 的 domain 不可以放0进去的，放0进去就不 define 了。
这样 I mean 如果是这样，
什么是 function？ 再回去 function 给你一个 input， 你一定要给我一个 output 的。
这样，因为听你这样讲话，这样 1 over n 它就不算
不 define on 0啊，
是啊，
它不 define on 0，它是一个 function define on 0到 infinity， 或者整个 real line 丢掉0。你要问它的 domain 在哪里，所以我们会 stress on domain。
每一个 domain 一定会 define 一个 exactly 的 point。
一定这是 function 的 definition。给我一个 input from 那 domain， 我都会给你一个 output。不会 undefined。我觉得你是不是 send 我一个 message 啊？你要讲 sign call 这个东西。
之前讲是怎样 define 那个
需要用到 differentiation 这样子。可是我们还没有碰到 differentiation， 所以碰到过后可能还会再 mention 一次。如果你要先看，你可以去 Prof Theorem 那本书看，或者 Patrick 那本书看。之后我们还会 roughly mention 一个。
都属于XM 的那个。
哎，你这
我觉得讲，我觉得日本会越来越小，越来越小。
那管那些时间，
当然了，知道不了小。
然后对，我也很看懂。哦，这本书需要让我背。对的。
对，我是一直他是他的主题，可能
就群里面整天在群里一直给加，因为
不要见面。
对啊。
这样不让这里加钱。
就是
这样他会帮你，所以帮你就是各种分解，都是比较高这边给你发有点钱。不管是想要在广州那边学下一个对，或者他或者写怎么样，电商还是写，还编程的，是你有这个时间来我是有的，想送高阶，我就单纯是这个互联网。这样
还有那个推荐那个专包的拿捏的那种品质，
这个做的这种这个。
这个嘞，这个没有人吃啊，这个。
再来。
咋的啦？
那情况那个很快。
我沙币。讲吗？他讲吗？我靠，嚣张啊，嚣张，很嚣张哎。
来，你看标。
LBC。Testing。啊？
还是波士顿最讨厌的。这还是波士顿，因为波士顿最讨厌的。
你的朋友哎，你忘记你的朋友了？
朋友啊。
啊？他不是有一个 IG， 你的朋友那个 motivation pop 啊？ 没有，他讲他很理智啊。Okay, should we leave this one first? Okay, what about if I replace this statement with open interval AB? What will go wrong? If I change open interval AB, what will go wrong? What will go wrong? I mean, change the closed interval into open interval AB. Oh, still can, right? Because Bolzano was not saying bounded only, man. So I still bounded by AB, man. Not maybe not less than equal, greater equal, but still bounded. Still can use Bolzano-Weierstrass. But the problem is when the Bolzano-Weierstrass might converge to A or B. Might converge to the endpoint. But endpoint is not included now. Okay, so maybe if it is open, right? Think of one example where the soup cannot be achievable. Okay? Cannot be achievable with a point inside. Right. I mean, let's give you one example. Give you one example. So in maths, you really need to draw. Okay, not just calculation. So A, B like this. Okay. And say your graph is like that. Like a McDonald's face. Okay. Where's the maximum here? Maximum here, I set it here. Okay. But this maximum here is attained at A and B. Okay. So no point inside X. So there's no point inside the open interval AB such that fx is equal to the soup. Okay, let's say this is Q. Okay, no X. So there don't exist X in open interval AB such that f of X equals to Q. So, okay, so Bolzano-Weierstrass still converge. You might converge to A or B, but A and B is not in my domain. Okay, I excluded. Okay. Okay, so this is a property of closed. Okay, quite important. Closed here. So you need to contain the limit. Bounded, you want convergence. Closed, you want the limit there. Okay. So if you will go to a general topology, this idea will be generalized. Okay, will be generalized. Okay. Yeah. So this is it for that one. So now we're gonna talk about limits now. Okay, we're gonna talk about limit because we want to introduce epsilon delta stuff. So limit points. Hopefully, we will finish continuity today. I hope. Okay. Let's consider one function here. So consider fx equal to sine 1 over x. Okay. You want to ask the question whether this function is how to say? First of all, this function is not defined as 0, right? Okay, because 1 over 0 is undefined. It's not but what's the limit toward? What's the limit towards 0? What happens if you take limit close to 0? So consider these two sequence here. So consider two sequences. Sn and Yn. Okay. In a moment, you'll see like quite weird, but if you sub into it, it's quite nice. So what's this two sequence here? This two sequence converge or not? Converge or not? For n large, these two should converge to 0. Okay, I just put different scalar on it. And what is Fsn and Fyn? Sure. What is sine of 4n minus 3 pi 4n minus 3 pi over 2? And what is sine of 4n minus 1 pi over 2? What is this two thing? You plot the graph out or not? For sine. Sine is what? Like this, right? Okay. So what are these points? So the top, the first maximum point is pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. Okay, so what is 4n minus 3 over pi? What is this? When n equals to 1, what happened? Over 2? N equals 2 leh? 5 pi over 2 lor? Where is 5 pi over 2? It's 2 pi actually. 5 pi over 2 is exactly pi over 2 plus 2 pi. Right. So what is this sequence here? Pi over 2 is 1, right? 5 pi over 2 also 1. Next one, also 1, because 12 minus 3 is 9. 9 pi over 2 is what? 2 pi. Okay. 9 over 2 pi is what? 2 pi plus pi over 2, right? So another full circle. So it's just 1, 1, 1, 1, 1 all the way. How about 4n minus 1 pi over 2? When n equals to 1 is what? 3 over 2. 3 pi over 2 is what? Minus 1. When n equal to 2, also minus 1. Why? 8 minus 1 is 7 pi over 2. 7 pi over 2 is what? 2 pi plus 3 pi over 2. Another full round of 3 pi over 2. So it's also minus 1. So what do you see here? I have this sine 1 over x. I take two different sequence converge to 0. I get different limit. So meaning what? Doesn't mean anything anyway. but what I want to say is even if we want to make it continuous, let's say we define it piecewisely. I want to define f tilde x to be equal to sine 1 over x. And this one works for all x except 0. I cannot define anything here such that it continuous, because already have two sequences that converge to different things. Okay. You know how this graph looks like or not? And we call this point singularity actually. We call this x equals 0 point is a singularity for this graph. Okay. So I mean, do you know how this graph looks like? Let me show you. This graph is like this. Okay. It keeps oscillating down, up and down, up and down, up and down, between 1 and minus 1. So you cannot just put one dot here, because it is infinitely close to 1, infinitely close to minus 1 on the other hand. Okay, so you cannot just fill in one point here. Okay. But let's look at the other one. Consider another function. So let's consider this function here. Fx equals to x sine 1 over x. Okay, so with the claim here is, you see this function here also not defined right at 0. Although x0 is 0, but sine over 1x still don't know. So what is 0 times infinity, for example? Can be 0, can be infinity, don't know. Okay, so it's undefined at 0 also. But we can say that f prime x equals to x for sine 1 over x if x is in real, no, 0, and it is 0 at 0, so this is equal to 0 if x equals 0, is continuous. I can just fill in that point, and then this function becomes a continuous function. So we need to show it. We need to show it. So for every other points, right, should be continuous. Okay. So take for a black box for a moment. Sine trigo function is continuous. Okay. Yeah. Otherwise, we need to prove it. Okay, let's take for a black box first. Sine is continuous. Okay. Okay, we know that 1 over s is continuous when every point other than x. Okay. And sine continuous everywhere. Take for a black box. So composition of them is continuous. X is an identity function, continuous. So product of continuous function, continuous. So only continuous for real line, not including 0. But now I include 0 here. I put in 0 point. And then I want to show that this function is continuous. So it's already continuous other than 0. So now what's left to prove is at s equals 0, also continuous. Okay? So this is the only thing we need to do. For all the other points, this one is a composition and product of continuous function is continuous. So we need to check this point, whether it's continuous or not. Okay. So suppose Sn converges to 0, and we want to show that Fsn is converging to 0 as well. Okay, to show that. So okay, let me write down at x slash 0 f tilde is continuous as f is continuous. Okay. Now, want to show f tilde is continuous at x equals 0. Okay. What to do here? So suppose Sn is a sequence converging to 0. Okay. Want to show that f tilde Sn also converge to 0. Which is what? Which is f tilde 0. Okay. How to do this? Do we have control of Sn or not? Do we have control of Sn or not? So so what? So what? So what? So what? You think? Sorry. Okay, 听好了。Okay, 来，一起回答。Okay, 来。So S0, you see Sn you want to converge to 0. How to converge to 0? Like this, right? Something like that. You can go for right, you can go for left or left, right, left, right, left, right, left, right. Okay. So meaning what? This Fsn, right, will sometime this one, 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 sometime this one. Correct. If you are not zero, then f of that Sn will be f. Okay. If you are zero sometimes, then your f tilde is zero. Okay. So altogether what? Altogether what? Not that Fsn is less than equals to let me put here. Is less than equal to 1. Okay, so I mean, so let's put here. So Fsn be okay, so like this. Let me look at this guy first. So what is this guy? Sine of 1 over x. Can you bound it above or below by something or not? Sine is bounded above by 1 and bounded below by -1. Okay, so I can bound this term here by xn minus n and what? Let me think. Okay. I think it's enough, right? Okay, so in particular, minus xn is bounded below by xn. Hey, sorry. So this implies that f of x. Sense? Does it make sense? Sense of? Does it make sense? Okay. And then, but what is Sn? We assume that it converges to 0. So let Sn converge to 0, right? If Sn converges to 0, minus Xn also converges to 0 because this is the limit law. Limit law. Yeah, limit law for sequence, right? Scalar multiple of convergence sequence converge to the scalar multiply the limit minus multiply 0. So you get 0. So the two of them converge to 0. The middle one have to converge to 0. Why? Squeeze theorem. Yes, squeeze theorem. Okay. So by squeeze theorem, Fxn also converge to 0, which is at 0. Okay. So you see, this function is special. When I add in the point 0 to define it, it becomes continuous. Do you know how this graph looks like? This graph looks like this. Laser gun. Like that. Okay. You see, they converge to one point, but this point is not defined by function. I put it in. So meaning I remove the singularity. Okay, I remove that singularity. Okay, I can just fill in this point here. Wait, become continuous already. Does it make sense? Previously, you see, this gap is so big. It frequently alternate between 1 and -1. I cannot fill in the whole interval here, you know. I can only put 1 point. Why? Because it's a function, I cannot define f1 to be an interval. Impossible one, right? Okay. Okay or not? Okay. So I can just fill in 1 point and make the original function continuous. Okay, so this leads to the idea of limits. Okay, this leads to the idea of limits. So let me define limit. So this leads to the idea of limit. So let f be a function defined on the interval f, sorry, on the domain df. Then C is a limit point of df if there exists a sequence. Okay? This is of sequence Sn, and these Sn's are the point in df such that this sequence cannot be x, cannot be C for every n, but Sn converge to C. Okay, think about this. Think about this thing first. Okay, I don't want to quickly pass by. So, what do you mean by C is a limit point? Okay, of df here. So you can find a sequence. Okay, that converge to C. Okay, so every point here is not equal to C. Why I put this kind of condition there? I can easily build a sequence that converges to C, you know. Which is what? I can easily build a sequence that converges to C one. Huh? What? What do you say? C1? C over n. No, C over n converge to 0, right? N to an n large. C over n. I can easily very easy constant sequence. Constant sequence converge to C. Okay, so I can always find some sequence converge to C, but this one nothing special. But what's special here is every term here cannot equal to C, and then converge to C. Okay or not? Then I only call this thing as a limit point. Does that make sense? If you want to be a limit point, there must be infinitely many things that converge to you, close to you. Okay, you cannot say I'm close to myself. No, you are not limit point. No one care about you. Okay, when a lot of people care about you, then you are. Okay or not? Does it make sense? Very important, very important criteria here. Xn not equal to C. If Sn can equal to C, I just take constant function enough. Oh, I'm the limit point of everyone. Nothing like that. Okay. If you want to be a limit point, it must be approachable by different points. Okay? Can or not? Okay. Think what is a limit point? What's a limit point? 有限的点 ，nice
是有些
华语应该叫做极限极限点，几点？几点？
要下课。
哎，时间为什么过这样快哦？可以讲2个 example 哎 ，right 是吗？哦 ，OK， 所以几点 ？OK， 几点 ？So if you want to be a 极点 ，okay, you must be approachable by different point. Okay, not yourself. Okay, you must be approachable by different. Okay, must be different. Otherwise, simply take constant function. Surely converge one. Right, but this is not our point. Okay, if you want to be a limit point, you must be approachable by different point. Okay, than yourself. Okay, then you are the limit point. Okay, and then next point. Okay, next point. If you cannot be approachable by other point, what do you call it? What do you call it? If you are not a limit point, you are not approachable by other point. What do you think? If you cannot be approached by other point, what do you think? Do you want to guess what point is that? Then you are pretty isolated. You are pretty isolated because no one can call you, no one can approach you. You are pretty isolated. So it's called a isolated point. Okay, or not? So you want to be a limit point or you want to be an isolated point? Which point you want to be? Sing. You want to be a limit point or you want to be an isolated point? Your point. I think you are like a limit point. Okay. Okay. So okay. And then sorry? Okay. So next. So the domain, the DF, is called close. Okay. Close if it contains all of its limit point. Okay. So for example, we call close interval, close interval, close interval. What's the close mean? So the close mean this one, it contains all limit point. Okay. So for example, show that the close interval is close. Show that the close interval is close. Close in this sense here contains all its limit point. Okay. So meaning if you are a limit point inside. So if you are a limit point of this closed interval here, then you are inside there. How to prove this? Sorry. If you are a limit point of this closed interval, then you are inside the closed interval. So what am I writing here is this. So this closed interval here is equal to the set of all limit points. It contains equal, let me think. It contains, so it's this direction. It contains all limit points. Okay. It contains. Let me think. It contains. I think the other direction is clearer about this direction. So you can show 1 and 2 actually. So 1 would say that AB is close. The close interval AB is close. And then you can see that actually the whole interval is the limit point of. Okay. Yeah. There are two things to show. For the first one, you need to show that it contains all limit points. And then the second one, you can see that actually everything here is a limit point. Okay. So the problem here is you need to show what are the limit points here. So what are the limit point definition? S is a limit point if there exists some sequence where all the sequence is not that limit point, but converge to the limit point. So meaning, if you want to show that it contains all the limit point here, what to do? Okay, so you need to actually show that anything less than A, anything greater than B is not a limit point. Okay, and then for every point inside here, you need to produce me a sequence. I think it's quite easy. How? For every point here, you could just take x plus 1 over n, for example. For anything strictly outside, for anything strictly outside, what happened? For anything strictly outside, what happened? For anything strictly outside, there must be an epsilon between them. If you have a sequence that converges to those points, you cannot avoid the epsilon. You cannot find points inside this set that converge to anything outside this interval. Can you understand what I say? You know? Okay. Let me try and draw this again. Real line is very important here. Okay, we want to show that any x in R which is not in AB is not a limit of AB. Okay, so maybe let's take this point here. Okay, let's take this point C. Or maybe let's take this point D. Right. But D and A, there's an epsilon. B and C also have a epsilon. If I have a sequence that converges to C, if I have a sequence that converges to D, then for every epsilon, I need to find something in the set that is inside here. Possible or not? Yes. Yes. How is it possible? My set is just here. Nothing here. You cannot find. Huh? So cannot converge, cannot find a sequence inside A that converges to D or converges to C. Correct or not? If you can do it, then that means for this epsilon, you need to find something in this set lie inside here, but not possible, right? Because my set is just going from A to B. So you cannot find. So they don't exist an Sn in this region such that Sn converges to D and Sn converges to C. Cannot. Because there's an epsilon here that you cannot find terms that lies in between this epsilon. Does it make sense? Or question or not? Question. Ask that. Suppose you can write a contradiction. Suppose you can find a sequence inside AB that converges to D. Means what? For every epsilon, there exists an n greater than or equal to n such that the xn minus D is less than epsilon. But can Sn exist here or not? Cannot, because my set is only from A to B. Okay, so there's an epsilon gap that you cannot go over. Okay, so this is a task for you to try and write this down carefully. Okay, I will write it out as well. Write it down carefully. Can you get idea or not? Ideas. Important in my class, you can get ideas. Okay. must get ideas first and then go and write down. Because the way of writing out, why I don't focus that much, you know why? Because 每个人都有每个人做事情的方式。OK， 我不想规定你做这个做那个做那个，但是我不想规定你怎么做，但是我会规定你做什么，但是怎么做 should be up to you。OK 了，这样的话才怎么说呢？才会 make sense to 你自己你觉得对你自己是最 make sense。OK 了，当然，如果你不能够很好的 make sense， 你可以先学其他人怎么 make sense。所以 that's why 我放很多 textbook 放很多不同的作者写的东西。哎，你去看哦，这个人这样写 make sense， 那个人这样写 make sense。OK， 老师这样写也 make sense。所以你要选哪一个呢？你选咯，你自己选咯。OK， 我就是这样，所以我就选到后面来，哦，原来我也可以有自己一套东西，这样自己写咯，你明白吗 ？OK 吗？所以这个就是你们大学需要训练的一个东西 ，OK 呢？所以为什么你父母老一辈叫你上大学，叫你去上大学，怎么上大学？读书这样辛苦，怎么还要上大学？就是要去学一些你自己学不到的东西哦。OK 吗 ？Otherwise 就是浪费啊。OK， 说现在要学的东西就是 try to make sense of yourself， 让自己合理化。OK 吗？可以吗 ？OK，I will also write this working down, but try and work it out also yourself. Okay, so this is about closed. So why closed interval is closed? Because it contains all its limit point. Okay, so this is like related to the open interval problem we discussed just now, right? If it's open, then maybe we don't find the maximum. Why? The Bolzano source might converge to something outside the set. But if the set is closed, all the convergence must happen inside the closed set. Okay, that's why the closed interval is closed. Okay, so the less than equal is very important. Very important. Okay. Okay. So another terminology. So next terminology. So let's talk about limits now. So if C is a limit point of df, we say that f has a limit L at C if fxn converge to L whenever Sn is a sequence of df take away C with Sn converging to C. Okay, so in this case, you write limit x to C fx equals to F. Okay. Have you guys seen the limit definition before in calculus? What sort of definition? Epsilon delta. Okay. So epsilon delta. Later we will see epsilon delta definition, but this one is a sequential limit. Okay. So meaning if so this picture, how should you think about this picture here? So let's draw it. So this picture is something like this. So if you have a C here, right, and then you have a Sn that converges to C, as S1, X1, X2, X3, X4 like that. Okay, converge to C. Then f of this guy, fx1, fx2, fx3, will converge to something we call L here. Does it make sense? fx1, fx2, fx3, etc. Okay. Converge to something in L. Then we will say that f has a limit at L. Okay. Any question? Questions? So if f has a limit at L, meaning no matter what sequence I take to C, okay. So this sequence of point cannot be C itself. Then f xn also converge to L. Then we will say that fx limit to L. Okay, no. So this limit here have to work for all sequence that converge to C. Any question? Later we will show, we won't show in class, but you can show that this is equivalent to the epsilon delta definition. What's the epsilon delta definition? Maybe we just say it now then. What's the epsilon delta definition? You guys recall no? F has a limit L if for all epsilon greater than 0, there exists a delta greater than 0 such that what? Such that what? S minus C smaller than delta, then fx minus L is less than epsilon. Is it complete or not? Complete or not? Is it complete? Complete or not? Not complete? What else you need? S in D, sure. Okay, sure. So such that for all x in DF. Like this, complete or not? This one is also strictly positive, right? You need strictly positive here. Okay. What else? Enough or not? Is it enough? So it has a limit at C. Okay. Sorry, here is 0. So you see now why this x minus C absolute value is greater than 0 here. Because I don't care when the domain point is equal to C. Right? Just now sequence. Sn cannot be equal to C. Here, same on this x, I don't care at the point C1. Okay or not? So one thing you can do is you show equivalence between these two. Okay, if I give you sequential limits, can you find a delta from here? Okay. If I give you epsilon delta, can you prove that there exists a sequence such that Sn not equal to C for all n, and then Fsn converge to L? Can you produce a sequence? Okay. Try and prove this equivalence, but we will do for continuity one in class. Okay, but this one exercise. Try show that sequential limit is equivalent epsilon delta limit. Try and do this because there's no more assignment to check you before midterm already. So try and do it yourself. We will prove for continuity, okay? But this one I left you for exercise. Okay or not? Okay. Okay. How about we break for a while? First, quite heavy, huh? Heavy or not? The content. Let's break now for pink guy. Okay. Break until 225. Until 225. Heavy or not? The material. Quite heavy, huh? Yeah, quite heavy. So what to do? Still need to learn. I think you guys are better. I mean, there are some worse. I'm not sure. They have this idea saying that certain people cannot learn certain things. Cannot, or it's not to say don't want, cannot. I think quite wrong. Quite wrong. I mean, I'm saying. I'm not sure. I'm not sure. I mean, because for the moment, for everything I do, is what I wanted to do. It's not that people force me, people ask me to do. So far, even if people force me, I go to do, at the very bottom, it's still because I wanted to do, right? And I will do it. It's not that like I don't want to do, but because you force me, I go and do. You can get the different concept here. No? There's something like people force you to do, then maybe you don't want to do. But at the end you do, right? But actually it's because you already accepted. Then you become you wanted to do. There's another way is you are forced to do. Okay? But you still don't want to do, but you do it because for the sake of people forcing you. It's not because you want to. You see a difference. Can understand the difference? Can understand the difference? Cannot. Maybe you never reach that stage. Huh? Maybe you never reach that stage. Yeah, I can think about it. Think about it. Mm.没有人要吃，没有人要吃啊。Very 你要喝的，可以。对，好。这个，
厕所还这是太大一点，打不好的真。
哪一个？那你大号小号都给人家看，就你大号小号都给人家看，没有，开玩笑，开玩笑。OK，我靠，谁呢？
下完了，有点不好意思。刚下完了考会那些又不好，不是不好，就是
没有那么好，
为什么讲？
确实。这样讲，你 remove 它没有？不是，没有，有两种嘛。你是 remove 掉它看不到你，还是你看不到它吧？哦，你们两个一起 unfollow，但是它还哦，除非你是 private，可能你 private 的话应该哦，对。不过我是这样啊，如果我不要看你，但是我不会逼你不要看我这样。
有点像那种骗 follow 的感觉。
这样讲
就是我 follow，因为他 follow 我们，follow 他，
没有啦，是他要认识你，他才 follow 你吗？
那有时候是我才
有什么问题？但是你要认识他吗？怎么你要认识他，他一定要认识你？诶？
假设你招刚流行收到对方来跑你的话，那种肯定就是不一定能够跑得回去嘛。
对呀、
没有，因为意思呀，你不会讲你会 unfollow 但不想看的人啊。
对，
你如果那人有 follow 我会一起要
我知道。怎么会讲？
follow 掉人家，那你把他留在你的粉丝。 啊，那你的粉丝才有在。
但是我的前提我不是为了他 follow 我才 follow 他。
啊，先留。
等一下，保住我。你有些人是就说一起聊，因为这里有三个人，
我知道
要拿合作一起哦。
在你涉及到我做很正是什么跟人家他们来。
对呀。
第三个。
那我的 IG 我甚至连看都不看，对吧
IG 连看就不看，看了啊，不是那个睡觉 story 哈。啊？哦，我只看到打球哦。
放到屏幕上看的小号，
放到屏幕上看。
我带入感觉不来。
Okay. Good. If I like team saying. Yes, okay. Okay. Suppose that you have two limit. What can we do with the two limit? You want to guess? Suppose you have. Add together. What else? Delete? Divide. Divide. Yeah, divide. And then? What else? Scalar multiply. Okay. And then? What else? What else? So here is limit of function already. We are dealing with limit of function, not the limit of sequence. So here is limit of function. So when we add function together. And of course, we can multiply function together and then look at the limit. And we can scalar multiply like what you say. And divide like Ethan say. So if I do all these operation, what happened? Sorry? If I do all these operation, what happened? What's the solution here? What's the solution? If I know my fx, the function, not sequence, function converge to L. Gx converge to M. Okay, what happened if I consider the sum? The limit law is the same as the limit law for sequence. So this is the limit law for function. Okay, so bear in mind, you need to separate these ideas. It's still limit law, but this one is the limit law for function. So L plus M, for example, for sum, if you multiply, then the limit also multiply. If you multiply function by k, also limit to scalar multiple of the limit. And the limit of the quotient is just quotient of the limit if M is not 0. Okay, so how to prove this? How to prove? For the first one, for example, for every sequence that converges to C, where the sequence is not C, the sequence of fsn plus gsn converges to L plus n. Converge or not? Conversion. Okay, let me write down. You guys still don't have the ability to keep things in your mind. So let's prove the first one. What to prove? Suppose Sn converge to C, where Xn not equal to C. Want to show Fsn plus Gsn converge to L plus M. Converge or not? Converge or not? Why? Why converge? What is the assumption? Assumption in this question. What do you know? What is L and M? Is the limit of F. M is the limit of G. So you know that if Sn converges to C, Fsn converges to L, Gsn converges to M. So you have two convergent sequence. So you can what? Add the two convergent sequence so that after you add, they also converge to the sum of the limit. So this sentence follows from where? Limit law of sequence. Okay, so all the propositions here also follow from the limit laws of sequence. Okay, so it's a different way to look at sequences. Okay, we use sequence to study function. So it follows from limit law of sequence. Okay. Okay, so all the rest is the same. You multiply together, product of convergent sequence still converge. Scalar multiple of convergent sequence still converge. Quotient of convergent sequence still converge. Okay, that one we proved already. Right, we spent a hard time to prove that. Why? We need to use epsilon, we need to use n to prove it. But now we just use it. Okay, we can just use it. Okay or not? Okay, so that's how we spend a lot of hard time using epsilon n to prove the sequence. Okay, so everything will follow the same. And there are some interesting theorem we want to look at. Maybe we don't want to prove. I think you are a bit tired already. So let's don't prove it first. If I don't prove it next time, then I just leave it in the notes. Okay, so theorem. But we will discuss how interesting it is this tree statement. Suppose f is a function on the domain df. I don't really care what domain is it. Just leave it as a domain. So first line, if C is an isolated point of df, then f is what? Continuous at C. If S is an isolated point, then S is continuous at C. Okay. Two way. If C is a limit point of df, which is in df, then f is continuous at C if and only if limit x to C fx exists and equal to fc. Right, this is what you learn in calculus. And equals to C. Okay. And the last thing is if C is a limit point of df, then limit x to C fx equals to L if and only if the function tilde define df union C by the following. Let me finish it. So if f is in the domain but not in the limit point, we just put fx, and we put L if x equals C is continuous. Okay, so this is like the example we had just now, the sine x times sine 1 over x. Okay, so x times sine over x, remember what happened? The laser gun, right? Okay, so if you replace the C as 0 there, what happened? You have a limit of fx to 0. If what? If I extend this function fx to that point with the limit which is 0 that time is continuous, then it has a limit to 0. Okay, if it has a limit to 0, then if I define this function is continuous. This is what we did just now, right? The laser gun. There's a limit go to 0, and then the f also going to 0, and I fill it in, it becomes a continuous function. Okay, so this is what that condition is doing. How about the previous one? 2. What 2 here? This one is very close. I mean, this is the same criteria you take to check continuous function is continuous, right? Because in calculus, how you determine a function is continuous? You need to take limit from the left, take from the right, and then equal to the value at that point, right? But ours is stronger, you know. This is stronger. This limit here is a sequence, any sequence to see on your left and right just sequence from left, sequence from right. My sequence can jump anyway. So this one is stronger, you know. Okay, not just left, not just right. It's any sequence. So my sequence can suddenly left, suddenly right. As long as it's converged to C, this guy should exist. Okay, so this one is pretty strong, stronger. So you need to think of this continuous here is as the sequential continuous for every sequence that converges f, Sn also converge. How about this point? I think this one is less obvious to you. I mean, maybe you never think about this kind of case before. What's this case here? If your C is an isolated point of df, then f is continuous there. How you imagine this? How you imagine this? How you imagine this? To show that f is continuous at C, what do you need to do? Every sequence that converges to C, you need to show that Fsn converges to Fc. But this one is an isolated point. Isolated point means what just now? How we define it? It is not a limit point. It's not a limit point means what? For every sequence such that Sn not equal to C, it doesn't converge to C. So there's no other points that converge to you. No other points that can converge to you. So what sort of sequence that converge to you? What sort of sequence can converge to C? Constant, yourself. That's the only sequence that can converge to you. I mean, ultimately, constant also can. At front, you can jump a bit, but at the end, must be just C only. Okay. In this case, this kind of sequence surely converge to FC, right? Because Sn at the end is already C. So Fsn converge to FC. You know? Okay. So you see continuity here, how to think about this continuity? If it's isolated, automatically continuous. But if this point is not isolated, maybe there are some other point around you, then you need to control their value of Fn. They cannot just straight away, I 1 here, 0 here, 0. Not continuous. No? But if you are the only one point there, whatever thing you do is okay. Correct or not? You see, if you are isolated, F is already continuous already. But if you are not isolated, you have something around you, and your F need to be continuous, you need to somehow control the F beside it. This is the last question I gave in your assignment, right? Can repeat the last question in the assignment. Okay. Huh? Can someone dig up what's the last question in the assignment? Very. Last question, the open interval.
Let F be defined on an open interval I and C in I. Prove that if F is continuous at C and Fc does not equal to 0, then there is an open interval J is a subset of I such that C in J and F of X is not equal to 0 for any X in J.
What does it say? Say, if you have a point it's not 0, okay. Around that interval, right? You can find a smaller interval such that every point there is also not 0. If you cannot do that, not continuous. Yes, question. Yes. Hey, a bit careful with your word. What do you mean by interval to be continuous? Still doesn't make sense. Continuous word for function, right? So what do you want? And then I mean, and you mean you want to take away the pre-image where fx equals 0? Oh wait, let me think. So you are like an interval with a hole like that, but this interval here just means that you can write it as it doesn't mention open or close or anything. Open. If it's open interval, then you need to write it as bracket A, comma B bracket. If you take out one point, then it's this interval take out some point, right? It's not an interval. So you need to find an interval. So open interval is like you can write it in the form of bracket A, comma B. And bracket. Round bracket. Okay. Square bracket is close. Yeah. I mean, the way I do this question, I can straight away tell you. I use contradiction. Yeah. I use contradiction. If you use contradiction, and then you can construct a sequence that don't give you the continuity. Okay, use contradiction. I think that one is the most pure question in this assignment, but if I'm not sure, can I have a look on the assignment? I think I also spent one afternoon to type out this question, this solution, this set of solution. Yeah. Okay, for this assignment, right, I would say question 3 and 6. Yeah, 3 and 6. Quite conceptual. 3 and 6. If you want to ask me which one is hard, it's 3. Others compute only. Number 5, you can look at my lecture example, then you modify, and this is the solution already. Right? Because I make it, in my assignment, in my lecture, I got like continuous and rational or irrational point, right? So you just make the rational, irrational point on this point, right? Correct or not? Correct or not? Yeah. Yeah. One, you need to play around with definition, but not too hard actually. Spell out what is soup, what is soup. And then two, I think pretty easy, two pretty easy. But I think Kwan Ye saw a problem here, right? You need to prove something. Or you use that one, huh? Two also probably also need that thing. So let me tell you a lemma. So lemma means a proposition. So if you have a number x less than epsilon, for all epsilon greater than 0, then this x should be what? You are smaller than all the positive numbers. You can be either 0 or either negative. So x have to be less than or equal to negative. This one will be helpful for 2. Maybe 1 also you need it. Yeah. Okay or not? You can prove this lemma. This lemma is not hard to prove. If x is greater than 0, then you can find an epsilon that is less than it. Greater than it. Okay. Proof is just very short, but you need to know how to use it. Quite important. Anything else you want to get in for your assignment? Question 3. Question 3, I think also use contradiction there. Suppose you have a convergent sequence, and then you will get contradiction. This is my way of doing it. Maybe you can try your way. Has no typically you need contradiction. Otherwise, how to say something that's nothing? How to prove nothing exists? You need to assume something exists first, and then say that that thing cannot exist, so there's nothing. Number 4. Number 4. Yeah, number 4 already tell you what's the limit. So just go and compute it. Just go and compute it. You will see that it is the limit. What's strange? Number 4. Why? Because you want to converge to A, man. So you need to take this guy minus A, take absolute value less than epsilon. So go and make this less than epsilon.
Assuming n of an just L. Should I write L as the ending point of the sequence?
Hey, wait, you talk about which question? Always got L. A. L is question 2. You mean question 2 or 4? Oh, 4A, okay. Yeah, so you bound it. Everything minus A, right? But you know an minus A, right? So there are n of them, or create n of them, NA over n. Huh? Wait, why? This n here grow with the n below. Correct. And then what are you trying to do?
It's a top.
Yeah.
And then n approaches infinity, an
Yeah.
But when I write down A, is A the last member of this infinite?
Infinite sequence.
Because
Why got infinite sequence here? Your Sn minus x is like fixed n, right? For n larger than bigger n. So why got S infinity here? Nothing. Huh?
I don't mean the S and maybe the sum.
Sum.
There's a sum of it.
No, there's a finite sum here. 1 to n only. For every n, this is a finite sum. For every n is a finite sum. Okay, no? For every n is a finite sum. Okay, I see some typo. For every n is a finite sum. Okay, 1 to n only. The dot is just to say that this n will change for all n. It's not plus dot nothing. If plus dot nothing, then that is an infinite sum. Okay, but this sum is stopped at an. Yeah, there's a plus there. Okay or not? For question, I think we should stop here. Let me think. What's L we left? Epsilon delta, squeeze theorem, uniform continuity. Hopefully, we can cover these 3 topics and then we have to go on differentiation next week, no matter how. Okay, we have left epsilon delta definition, proof, equivalence definition, squeeze theorem for function. Again, last time we have for sequence, now for function. And then last thing is uniform continuity. This is very, 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 very important. Again, when you first see analysis, uniform continuity. Yeah, so you can see me now, okay, for assignment. Let's go to my office. Okay, you want to discuss about assignment. All right, so see you tomorrow morning.